VF1 and forward voltage drop of diode 2 is VF2. So you will equate the two voltages, that's all, right? And then you would be able to calculate how to arrive at R1 and R2 so that you are not having huge discrepancy in the currents, right? Okay? So much so for power semiconductor diodes. Any questions on this? Yeah. So in fact you can start looking at RSH1 equal to RSH2, that's not a problem. So you can take the same values for both so that you are protected against any eventuality. Whether one leakage current, that's a good question. I hope you got his question. He was telling that if I start assuming that the leakage current of this is higher than the leakage current of this and I do all the calculations and I get some RSH1 and RSH2. If in actual real life it is the other way around, then how do I make sure that the voltages divided between the two diodes are still within the limits? So if you assume RSH1 equal to RSH2, then you can just do the calculation for the safety measure as to what is VD2 minus VD1. So you can use the same resistance across both the diodes. It will work. One more thing is, most of the times we tend to test at least a few diodes from a batch before we start using them, generally. And we will also make sure normally that the diodes are characterized as much as possible. Especially when you are using them in high power applications, we would not like to take a chance. Whenever we talk about high power drives, especially motor drives, almost 50 to 60% of the processor time goes towards protection. Rest of 30-40% only really goes towards control of the devices. 50 to 60% is going towards protection means we are really worried about the life of each of these devices, because each of the device can cost crores of rupees. That is the reason we'll have to be extremely careful about the devices. So we would definitely characterize each of them normally, especially when we talk about very, very high power applications. When we use it in milliampere or even ampere applications, we don't care much. That's why power supply applications, we don't care so much about the life expectancy. Whereas high power applications, we worry too much about life expectancy of those devices and converters. Right? Yeah. Here. See, because the current actually is stopping, we are expecting that there will be a very high LDI by dt. But we are limiting basically the dV by dt by having an RC value. So we are having probably some load current flowing from here, from power supply is here, from through this it is flowing like this. Eventually the capacitor will get charged and no more current will flow. Maybe there is some other path for the load current. I am only showing the part of the circuit. So this is taking the brunt of the diode turning off, and it is trying to take the entire current, because of which the capacitance is getting charged. And the rate of charging of the capacitor in this case is a constant, because the current is constant, right? So you are going to have a linear rise in the voltage, which will also make this voltage across the diode not go up drastically. So you are essentially averting any chance of the diode breaking down because of the sudden increase in the voltage. That's what happens, right? Maybe I should have shown this here. I think that's where the problem lies. This should have been shown here. Then I think things are better, because the inductance current now also is not abruptly removed. Sorry about this mistake. I should have definitely shown this here. What you ask is right, because the inductance is in series with the diode. Nothing is averting it from getting the brunt of LDI by dt. Right. So this connection should have come here before, like between the inductance and the diode. It can't come after the inductance. Doesn't make sense. Right? So as far as silicon controlled rectifier or SCR is concerned, this is basically a 4-layer device. We normally say about diode as a 2-layer, P and N. Transistor is a 3-layer device, PNP, NPN. Whereas this is a 4-layer device. So I'm going to have PN, PN. This is how it is going to be. Okay? And these two portions are heavily doped normally. This will also be plus. This will also be plus, which means heavily doped. These two are heavily doped normally. So they are like the emitters of any transistor. Transistor emitter will be normally heavily doped. So this is how it is going to be. And I'm going to have this as the anode and this as the cathode. And this will be the gate. So this is a 3-terminal device with an anode, cathode and a gate. And this is junction 1, J1, this is J2 and this is J3. When we apply plus here and minus here and no power supply to the gate, I'm going to have J1 and J3 forward biased, right? Because J3 is towards N and it is going to get a negative voltage. So J3 will be forward biased. J1 will also be forward biased because P is connected to positive, whereas J2 will be reverse biased because this N is closer to positive, this P is closer to negative. So I'm going to have, for this kind of power supply, J1, J3 will be forward biased, whereas J2 will be reverse biased. So the blocking capability of this device heavily depends upon J2, especially when I am in forward biased condition. So forward blocking capability of the device heavily depends upon J2. If J2 is really not strong enough, it will not have the forward blocking capability properly for this device, right? Whereas when anode is having negative and cathode is having positive power supply, then I'm going to have it the other way around. J1 and J2 will be, J3 will be reverse biased and J2 will be forward biased. So reverse blocking capability heavily depends upon J1 and J3 in this case, right? Now if I look at this device, this is like a PNP transistor connected to an NPN transistor. Only thing is that this base is going to be common with the collector of the second transistor. Similarly, this base is going to be common with the collector of the other transistor. So it is like two transistors connected back to back. So I'm going to have, basically, let us say this is a PNP transistor like this, right? So I'm writing this is P, this is N and this is P. And I'm going to draw one more transistor where this is going to be the emitter and this is the collector, right? So this is again N and this is P and this is N, right? So this happens to be my cathode and this happens to be my anode. Now this N is connected here. Similarly, this P is connected here. Right? So this is essentially the thyristor configuration or SCR configuration. Now this is my gate terminal. So if I don't give any power supply to the gate, if I don't forward bias it, I'm not going to have this transistor conducting at all. But the moment I actually inject a current into this, gate current into this, or if I forward bias this, then this transistor is going to conduct. So I'm going to have the base flooded with huge amount of charge carriers. The emitter is heavily doped, so I'll see a huge amount of electrons coming in, and then that is going to go through the collector and that is going to flood the base of the next transistor. So I'm going to have essentially a small base current here in this transistor, which is coming in the form of gate current, will actually make a huge current flow through the collector, and that is going to flood the base of the other transistor with a large number of charge carriers. So I'm going to have that again passing through the collector in the form of a large current. So it is like a, huge amount of runaway condition. A very, very large current is going to be generated with a very, very small gate current being injected in this side. And once you start the conduction, you don't have to do anything further. Even if you remove the gate drive, because of the amplification, repeatedly happening within the two transistors, the device is going to continuously conduct, whether I like it or not. Initially, you just need to give a small, trigger. The moment you give a trigger, this will start conducting. A large collector current will flow, which will flow into the base of this transistor. So again, a large collector current would flow. So this will become a loop here, basically. So we will see that the thyristor conducts with a very, very small trigger. An SCR just will be able to conduct with a small trigger in the form of a gate pulse. The moment it starts conducting, it will be very difficult to quench the device because it is essentially increasing the current further and further. The current overall passing through the anode to cathode is limited only by the power supply that I am connecting, and if at all I connect the load here, that is going to limit the current. Otherwise, there is nothing else that is limiting the current within the device, basically. Right? So that is the reason why SCR can be controlled only for the turn on and cannot be controlled for the turn off. For turn off, it is very difficult to, really bring the device into off condition. It's not going to be easy. That's one reason why thyristors find or SCRs find extremely large number of applications in rectifiers, not in inverters, not in choppers so much. Because with DC supply, it will be very difficult for us to turn it off. And inverters and choppers always have DC as the input. Choppers convert DC to DC and inverters convert DC to AC. So if I have input as DC, I will not be able to turn off the device, and that's one reason why I would like not to use SCR as much as possible in DC input circuits, as much as possible. Right? We would like to use IGBTs or MOSFETs or IGCTs or GTOs and so on. Those things are used more in the DC circuits, not in AC input circuit. AC input circuits generally use SCRs or diodes. So this is the basic working of a thyristor. So if I look at the characteristics of the thyristor, the symbol of a thyristor is somewhat like this. So this is exactly like a diode, but there is an additional terminal. So this is the gate terminal, this is the anode, and this is the cathode. So this is the symbol of a thyristor. So it is exactly like a diode, but with a gate. That's it. So as far as SCR is concerned, if I look at actually increasing the forward voltage further and further, beyond a particular point, J2 will not be able to withstand any more voltage. At that point, it will break down. So that particular voltage is known as forward breakover voltage, FBO, forward breakover voltage. If I don't give any gate pulse also, if I increase the voltage further and further beyond the withstand capability of the SCR, it will start conducting, it will break down. So it will be a destructive breakdown normally. What I mean is it will not come back to normalcy. It is gone. That's it. You have overloaded it. So you will have normally this as the forward breakover voltage. So normally what will happen is it will just go like this and then it will go like this. The characteristics go like this. So it will go until the breakover point. Then there will be like a negative resistance characteristics which is transient, which we will not be able to observe normally, and then it will just take over as a normal diode. Like as you increase the current, very slightly the forward voltage will increase. This is how it will be, right? Whereas on the reverse side, again there will be a reverse breakdown voltage. Until that point it will be literally zero current. After that, if you increase it, the current is going to increase. So this is reverse breakdown voltage. So on the positive side or the forward side, we call it as forward breakover voltage, and on the other side we call it as a reverse breakdown voltage. This is without any gate current. If I give a gate current pulse or gate voltage, positive forward biasing of the gate, this can happen at lower and lower voltage itself. So I should show it as though it happens at much lower voltage. So this happens, this will go a little bit and then it will come down drastically. Once it starts conducting, immediately you are going to see that the voltage drop across the device decreases drastically, right? So if I increase the gate bias, the conduction can happen even at lower and lower voltages. That's what it is indicating, right? If I give a gate pulse of 15 volts, for example, if it starts conducting once the anode shows 100 volts, maybe if I give the gate voltage of only 10 volts, you have to increase the anode voltage to 120 volts or 125 volts. Only then it will start conducting. So you have, the gate bias also reduces. Higher the gate bias, we can have the conduction started even at reduced anode voltage, less amount of anode voltage, right? So if I give higher and higher gate bias, I will be able to make the device conduct at lower and lower anode voltages normally, right? So this is essentially the VI characteristics of the SCR. Now, if I actually allow the anode current to go until, let us say, 10 milliamperes or 15 milliamperes, and I increase the voltage further and further, anode to cathode voltage further and further, I am going to have more and more current flowing through the device. If I just allow it to go until 10 or 15 amperes and I abruptly bring down, I don't give the gate voltage anymore, it may not latch into conduction. There is a minimum anode current for which the device would be latched into conduction. That particular current is known as latching current. What I am trying to get at is, let us say I have a device, I have given maybe 150 volts across the device, anode to cathode. I have not given any gate current. It has not started conducting. Now I am giving a gate current. I have connected a load in series with the SCR. The current has increased to 10 milliampere, maybe 15 milliampere. I have removed the gate pulse. Now if I look at the current, it will be zero because it has not latched itself into conduction. I have gone to now 20 milliampere as far as the anode to cathode current is concerned. At that point, even if I remove the gate pulse, still the device will continue to conduct. So, at what minimum anode to cathode current the device is latched into conduction and it stays conducting, even though I may remove the gate pulse. that particular current is known as the latching current. The latching current is the minimum anode current at which the device would stay put at conducting condition even though I would remove the gate pulse. That is known as the latching current. Because I will require minimum amount of charge carriers to be present in all these junctions. Otherwise, it's not going to work. That's the reason, right? So, latching current is one of the very important parameters in thyristor. When we actually design the thyristor circuits, we have to take care of this, that at least this much current flows through the device so that even if I remove the gate pulse, it will continue to conduct. We'll continue with SCRs in the next class.